today. I'm J Wildberger, and today we're going to look at why infinite sets don't really exist. I'm going to start to try to explain that, even though it's a very controversial position and most of my fellow mathematicians will not agree with me. Let's first talk a little bit about regular set theory, which is a useful addition to our tool chest. A set is a collection of mathematical objects. And it's agreed that all the objects in a set have to be distinct, and the order in which we present them is unimportant. So here's a set, 1, 3, 5, 7, 9, happens to be the set of all odd numbers less than 10. It has 5 elements in it, because we can match each one of the elements with a 1, so we have a string of 1s, which we usually call 5. So we say the size of S is 5. Here's another set, P, which consists of the prime numbers less than 10. Its size is 4. There are two fundamental things we can do with sets. We can take their intersection, that is, create a new set which consists of those elements which are common to both sets. Or we can create the union, which is the set of elements which are either in one set or in another. So this kind of set theory is useful and very practical, but in 1870s, George Cantor, a German mathematician, introduced a dramatic new suggestion. He said, why don't we consider also infinite sets? This caused a lot of consternation, it caused a lot of discussion and controversy, and it ultimately became a very popular way of thinking about a lot of mathematics, so much so that it's now the orthodoxy. Let's have a look at the simplest example of an infinite set, according to Cantor. Here is the set that's usually called M, standing for natural numbers. It's a set whose elements are all the natural numbers, all in quotes. 1, 2, 3, 4, 5, 6, 7, 8. You keep going and keep going and keep going till the end of time and beyond, and all the natural numbers are contained in those brackets. That, according to Cantor, was a new mathematical object, which is now on a par with, say, the number 5, or the set S that we defined earlier. We can manipulate that object, we can use it in other mathematical formulations, we can do things with it just like we can with numbers. Well, this was historically very unprecedented. For thousands of years previous to Cantor, people had been very nervous and respectful about the magnitude and the immensity of infinite sequences. So to the ancient Greeks, for example, the natural numbers were a sequence that progressed beyond our view. Looking further and further in the sequence requires more and more powerful techniques. But nowhere can you enclose all of those integers in a completed whole. That was the traditional point of view. But Cantor said, no, we can. And not surprisingly, he generated a lot of controversy. There were many very prominent opponents of Cantor's theory, including Kronecker, Mittag-Leffler, Poincaré, Brouwer, Weil, and others. And this list includes some of the greatest mathematicians of the last 100 years. It became clear also that Gauss, who lived before Cantor's time, had also expressed an opinion on these matters. And he was also opposed to the idea of considering infinities as a completed whole. On top of these objections, Cantor also had to deal with paradoxes. People started to discover paradoxes in the new theory that Cantor had created. So there are famous paradoxes due to Burali-Forti, to Russell, and indeed to Cantor himself. So by the year around 1900, the new theory was immersed in difficulties and was being attacked in all sides, and at that time it probably looked like it was doomed. Alright, now if we fast forward to 2009, we find a remarkable change in circumstances. Now infinite sets are universally acknowledged as making sense. Almost all modern mathematical objects are defined in terms of infinite sets. So this object here, which many of you will recognize as a circle, According to a pure mathematician, this is actually an infinite set of points. Can't see them all, but there are actually an infinite set of points there. A square, that's also an infinite set of points. So is even a lowly line segment. A torus or donut is an infinite set of points. A function like f of x equals x squared is defined in terms of an infinite set of points. If a mathematician looked at a tomato like this, probably they would see an infinite amount of tomato points. How can this come about? How is it possible that there was such a dramatic change? Well, in my opinion, it's because of voodoo and distortion of mathematical logic. Currently, we have a theory of so-called axiomatics, where mathematicians build philosophical castles in the sky. And they proclaim that these make sense because they say, well, let's just assume that they do. We'll assume that they do by stating certain axioms that will phrase in mathematical language to make them sound relatively legitimate. Most modern mathematicians do not understand these axioms. In fact, they hardly even ever use them. There's only a small cohort of mathematicians that do. But nevertheless, everybody pays lip service to them and acknowledges that no doubt they are correct. It's one of my purposes to take the air out of this inflated theory and to bring it down to earth. Right now, however, is not quite the time to do it because this entire development requires a little bit more sophistication and more careful analysis. What I do want to show you, however, is that even if we restrict ourselves to the natural numbers, an ordinary person can appreciate that it doesn't make sense to talk about this as a completed whole. And the way we're going to do that is by looking at bigger and bigger numbers. Once we do that, then we get an appreciation for just the immensity of this infinite sequence. So next time, we're going to look at the natural numbers and extremely big numbers. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.